Hello, students. I hope you're all having a good time at home. Today, we are talking about sketching the graph of a function in section 3 of chapter 4. In last lecture, we talked about the concavity of a function. We talked about the inflection points and those procedures, those concepts that we will use today in sketching the graph of a function. Let me give a quick review. We said when we are talking about the first derivative, about increasing, decreasing, criticals. When we are, critical numbers, of course, increasing intervals, decreasing intervals, critical numbers, local extrema of a function. We were using the first derivative of the function, okay? So when a function is given to us and it's required from us to find their increasing, decreasing criticals and local extrema of the function, we were using the procedure on the first derivative of the function. And when it was required from us to find the concavity, of course, concavity, we have got concave up and concave down of a function. And the inflection points, we were using the second derivative to do our procedure or to find the concavity of those functions. Today we are coming to this sketch of a graph of a function. We have got some procedure for sketching the graph of a function. We have to do them one by one, or else we may have some mistakes if you are not following the procedure. The first thing that we have to do while sketching the graph of a function, of course, later on we will do it by an example. The first thing that you have to know is the domain of the function. You have to describe the domain of the function. If you do not know the domain of the function, how would you know where to sketch the graph of a function? Whether it is from negative infinity to infinity or on an interval, you have to specify the domain of the function. That is very important. The second thing that we need to know, if it is possible for the examples that will be given to you, find the intercepts, okay? Intercepts for the function. What are the intercepts? You know that we have got X-intercept and Y-intercept. What is X-intercept and Y-intercept of a function? X-intercept, that is the intersection of the graph of the function with the x-axis, and Y-intercept is the intersection of the graph of the function with the y-axis. Of course, how do you find X-intercept? We are putting y is equal to 0. You have studied this one. And for finding the y-intercept, we are putting x equal to 0 in the function that we have got. Then we have to find, not we have to find, if it is possible, of course, when I'm talking about this procedure, you're finding those that are possible for your example to find. So the third one is to find the symmetries, okay? What is symmetry? How many kinds of symmetry we have got? We have got symmetry about y-axis, okay? You know that if the function is even, we have studied this one. If you have got an even function, then the function is symmetry about the y-axis, and we have got symmetry about the origin, okay? Symmetry about origin, if we have got the function is odd. So if the function is even, we have got symmetry about y-axis. What does that mean? Symmetry about the y-axis, that is y-axis. That means whatever I'm sketching on that part of the y-axis, it will be reflected on that side, okay? Symmetry about origin is whatever I'm sketching here, I will have it at the other side of the Cartesian coordinate, and you're familiar with those things. Okay, symmetries, and then if it is possible, find the asymptotes of the function. Okay, how many kinds of asymptotes did we have? We had vertical asymptotes. Let me write it here. We had vertical asymptotes, we had horizontal asymptotes, and we had slant asymptote. Okay, or we were saying oblique gives the same meaning. Oblique asymptote or slant asymptote. We had vertical asymptote. How were we finding a vertical asymptotes? We were setting the denominator of the function equal to 0. Then we were finding the limit of that function as it was as x was approaching to those numbers that were making the denominator equal to 0. If we got the result was infinity or negative infinity, we would say that that point is a vertical asymptote. For the horizontal asymptote, we were setting the limit. We were finding the limit of the function approaching to infinity or negative infinity. If the result was a number, we would call that number a horizontal asymptote. We have studied those things. Slant or oblique asymptote, we said the power of numerator must be 1 greater than the power of the denominator. Only 1, okay? The power of numerator must only be 1 greater than the power of denominator. Then we can say that the function that we have got has got slant asymptote. And of course, we were using long division to find slant asymptote. So if it was possible for the example that you have got, you're finding the asymptotes of the function also. The fifth one, we are finding f prime. Okay, why do we find f prime? To find increasing and decreasing intervals. Okay, to find critical numbers and to find local extrema. That means maximum or minimum points. Extrema. We were using the first derivative to find increasing, decreasing critical numbers and those things. And then we are finding the second derivative of the function to check whether the function is concave up or down. That means we are finding concavity and inflection points. Okay, inflection points. Then find or plot some specific points. Okay, plot some specific points. What does that mean? Plot some specific points on the Cartesian coordinate. Of course, when we are sketching the graph of a function, when you are doing those procedures, you have to find you have to sketch the Cartesian coordinate, and on Cartesian coordinate we are plotting some points. What are the points that we are plotting? Critical numbers is good to plot on the Cartesian coordinate so that you see where the function is increasing, decreasing, and you are using the procedure to find the concavity and the intercepts are important to be put on the Cartesian coordinate so that you are having a good sketch for the function that you have got. And then of course we are when we are doing all those procedures, that's 6, 7. Sorry for that, and that is number 8. 8th procedure is that we are sketching the graph of the function, of course on the Cartesian coordinate. Let's do this one on an example, on a given example. Let's see how this works on an example. The first example that you have got in the course material, we have got, it says example 7, of course, sketch the graph of, or I do not need to write sketch the graph of, or simply I will write a sketch f of x that's equal to x to the power of 4 minus 4x to the power of 3 plus 10. Okay, so what is the function that is given to us? It is x to the power of 4 minus 4x to the power of 3 plus 10. We have to find all those things on the function. Okay, then we can do the procedure, or we can sketch the graph of the function. The first thing that we have got is to find the domain of the function. Of course, as I told you, if you are not sure with the domain of the function, how would you know where you are sketching the graph of the function? So the domain is really important. What is the domain of that function? If you look at the domain of this one, it is a polynomial. Do I have any point that makes this function undefined? No, of course, I do not have any point. So the domain of the function, okay, is equal to the set of all real numbers. Why the set of all real numbers? Because whatever point I'm inputting into that function gives me something defined. It doesn't make a problem for me. Positives, negatives, rationals, irrationals, doesn't make a difference for me. Okay. The second one, we are finding the intercepts. Let me find the intercepts. For finding intercepts, let me write the intercepts so that you know what we are doing. How do you find intercepts? The first thing that I have got is to find the y-intercept. Okay, we will find y-intercept. To find y-intercept, we put x equal to 0 into the function. Okay, so what will we get if you put x equal to 0? So y, that is the f of x, is equal to 0 to the power of 4 minus 4 multiplied to 0 to the power of 3 plus 10. What is the result of this one? That's equal to 10. So what is the point that I have got here? It is the point 0. I set 0 into the function. I put instead of x 0. And what did I get? I get 10 out. So that is the y-intercept. The function that I have got is intersecting y-axis at point 10. Okay, so the point that I have got is 0, 10. Let me see if I can find the x-intercept, okay? Because sometimes it's hard to find it, so we'll just leave it like that. Why? Because you do not know the procedure, so how can you find it? It's not easy for you to calculate it in your mind. You need a calculator, and since calculators are not allowed for you, so you're not supposed to find it, okay? So we are putting y equal to 0. When we put y equal to 0, that will be x to the power of 4 minus 4x to the power of 3 plus 10. Since this one is not an easy equation to evaluate for you, and you haven't studied the procedure for finding x to the power of 4 if you have got an equation like that, so skip this one. Okay, skip it. Do not find the x-intercept because it's not included for you to find something complicated like that for you. Okay, let's move to the other point. What is required from us? Okay, we found the domain, we found the intercepts. Of course, we found y-intercept and couldn't find the x-intercept because it's a little bit hard for you to find. We are coming to the symmetries. The third point, we have got symmetry. Let's see if you can find the symmetry of that function, or the function has got symmetries or not. We are checking for the even and odd function. Let me put f of negative x into the function and see if the function is odd or even. If I put negative x into the function, what will I get? I will get that thing. Of course, instead of every x, what shall I input? I'll input negative x. So that will be x to the power of 4 plus 4x to the power of 3 plus 10. Is that equal to, does that equal to the original function? Is it the same thing as the original function? No. So it is not even. Okay. Is this function equal to negative f of x? That means if I put a negative in front of this one or take a negative out, what will I get? I will get negative x to the power of 4 plus 4x to the power of 3 minus 10. Is that negative f of x? This one? No, it is not also equal to negative f of x. So the function is not odd. Since it's not even and it is not odd, it's none of them. So we say that the function is not symmetry. It's not symmetry. About of course, when I'm saying it's not symmetry, I mean about y-axis and about the origin. What is the fourth thing that we have got? We did those asymptotes. We have got vertical, horizontal, and slant asymptotes. So the fourth thing is asymptotes. Okay. If you look at that function that we have got for vertical asymptotes, do I have any, do I have got a denominator? No, I do not have it, since I do not have denominator in that function. So there is no number that makes it undefined, and I cannot find vertical asymptotes for this. If I set limit approaching to x approaching to infinity or negative infinity, do I get a number? No, I do not get a number, so it doesn't have horizontal asymptote. And since I do not have power of numerator greater than the power of denominator by 1, so it doesn't have asymptotes. Okay, does not have asymptotes. In general, having polynomial functions is easy to sketch the graph of them. Why? Because the domain is easy, intercepts finding them is easy, symmetries are easy, and asymptotes are also easy to find. And mostly they do not have asymptotes. If you have got, not mostly, in every example, if it is just a simple polynomial, you will not have asymptotes in it. But this asymptotes, symmetry, asymptotes always occur when you have got a fractional a function. Okay, the fifth step is to find f prime. When I'm saying f prime, I mean about increasing, decreasing, and everything that I need to proceed in the first derivative. Okay, so I need to find f prime of the function. That means the first derivative of the function. Let's find f prime. F prime is equal to what? Is equal to 4x to the power of 3 minus this one. 3 comes down, multiplied to 4. That's equal to what? That's equal to 12. Okay, minus 12x squared, and the derivative of 10 is equal to 0. So I will simply not write it. Okay. Now we are finding the critical numbers. How do I find critical numbers? Of course, I'm setting f prime equal to 0. What does that mean? That means 4x to the power of 3 minus 12x squared is equal to 0. Okay. Now, this is a simple equation to be solved. So I'm simply writing 4x to the power of 3 minus 12x squared. Taking out the common factor, I have got 4 is common between them, and x squared is also common between them. So what remains here? If you look at the function, here x remains minus, and here you have taken 4 out, so 3 remains. You have taken x squared out, so nothing remains from the x's. So that's equal to 0. Let's simplify it more. I mean, let us solve the equation. So 4x squared is equal to 0, or x minus 3 is equal to 0, because it's multiplication of two parts. Either this one is equal to 0 or that one. From here, I get that x is equal to 0, and from here I get that x is equal to 3. You know that simply dividing both sides by 4 and taking the square root, I get x is equal to 0, and this is, I'm taking simply this one to the other side, I get x is equal to 3. What is x equal to 0 and x equal to 3? These ones are critical numbers. Okay, these are critical numbers. Previously, we were leaving critical numbers just like that, but it is better to calculate it. Okay, here, or later I will do it. At the end, I will do the calculation so that you will not mix it up with the other procedures. Okay, previously, when we were finding f prime of the function, okay, when we are finding f prime of the function, we were finding the critical numbers, and then we were putting those critical numbers on the real number line. Why were we doing that? To find the increasing, decreasing intervals, to find the local extrema of the function. So now I'm putting 0 here and 3 there. Now what do we have to do? We have to take test numbers. What are test numbers? I said when we are putting critical numbers on the real number line, it divides the real numbers into sub-intervals. An interval that's from negative infinity to 0, an interval that's between 0 and 3, and an interval that's greater than 3. So I'm taking a number in that interval. I will choose -1. As I told you, we are always choosing a number that's easy to calculate. I'm choosing a number between 0 and 3. I will choose 1, and a number greater than 3, I will choose 4. Okay, now we are putting those numbers into the first derivative of the function. Of course, I told you to put it in the factorized one because it would be easier for you to calculate. Okay, if I put -1 into here, what will I get? Let me write it for you here. I have to find f prime of -1. I have to find f prime of 1 and f prime of 4. Okay, prime of -1, of 1, and 4. Okay, if I put negative 1 into here, I will always get something positive from this part. Okay, it is positive. Why? Because I have got x squared here. So if I put negative into here, I will get positive because it's x squared. If I put negative 1 into x minus 3, what will I get? Minus 1 minus 3, it is something negative, so I will get a negative out. Okay, since it is negative, that means whatever number I'm choosing from here is negative. What does negative mean here? That means the function that I have got here is decreasing. Okay, let's put 1 into the function. If I put 1 into here, of course this part is again positive, so that will be positive. If I put 1 instead of that x, 1 minus 3 is again negative. So positive multiplied to negative, it's again negative. What does that mean? That means this interval is negative. Whatever number I'm choosing, I get a negative value out. What does that mean again negative? That means the function that I have got is again decreasing. Okay, f prime of 4. If I put 4 into that part of the first derivative, I will again get positive because of the squared. And 4 minus 3 is positive. That says positive multiplied to positive. I get something positive. So whatever number I'm choosing from that interval, I will get something positive. What does positive mean? That means the function that I have got is increasing in that interval. Now what's remained here to check whether this one is local maximum or local minimum. How do I know that? Of course, critical numbers become local maximum and local minimum. If the sign changes from left to right, it will become a local extrema. If it doesn't change, so it is not a local extrema. If you look at 0, the sign is negative, the sign is negative. Since the sign doesn't change, it is just negative, so it is not local extrema. Okay, it's not max, not min. Let us look at 3. If you look at 3, from the left side, the function that we have got is decreasing. Then it starts to increase. So what is that point? It is local minimum. It's the minimum point for the function. Okay, now we did find the increasing, decreasing, critical numbers, and the local extrema of the function. Now what do we have to do? Where is the procedure? Okay, we found those things. We have to find the sixth step, the second derivative of the function to check whether the function is concave up or down, and find the inflection points of the function. Now we are finding the second derivative. That is procedure number 6. Okay, we are finding f double prime. If you want to find the f double prime, if you look at the function, f prime is this one. So finding f double prime is equal to what? That will equal to 12x squared. I have got minus, that will be 24x. Okay, that's the second derivative of the function. Now we have to find again those numbers that makes the second derivative equal to 0 or undefined. We don't have anything that makes it undefined, so we are simply finding those numbers that makes it equal to 0. But here we do not call them critical numbers, we do not call them inflection points. We are just finding them because in the first derivative we are calling those numbers criticals. Okay, do not forget about that and do not mix them up. Okay, this is again an equation. I'm taking the common factor out. 12 is common, x is common. Here x remains, minus here 2 remains. That will equal to 0. Again, 12x is equal to 0, or x minus 2 is equal to 0 because I have got multiplication of two parts. Either this one is equal to 0 or that one is equal to 0. From this one, dividing both sides by 12, I get x is equal to 0. And from this part, when I'm taking 2 to the other side of the equation, I get x is equal to 2. Look here, I'm not calling them critical numbers from the second derivative. Just in the first derivative, I'm calling those numbers criticals. But we are doing the same procedure as we did for the first derivative. I'm putting them on the real number line to check the concavity of the function, okay? So what are the numbers that I have got here? I have got 0 and I have got 2 for the second derivative. Please do not put them on the same real number line because you will definitely make mistakes. Okay, now Again, we have got sub-intervals. Intervals that are less than 0, I will choose -1. Intervals that are between 0 and 1, I will choose, 0 and 2, I will choose 1. And from that interval greater than 2, I will choose 3. Again, what do we have to do? We have to find f here double prime, okay, of the function. Okay, we have to find f double prime of -1. Look, previously we were putting it in f prime, but here we are putting it in f double prime, f double prime of 1 and f double prime of 3. Now we have to calculate, not calculate, find the values, the sign of the f double prime. If I put -1 into the factorized form of the second derivative, what will I get? 12 multiplied to -1, that will be negative, okay? -1, -2, that will be negative. So the result is what? It is positive, okay? Since it is positive, what does that mean? That means the function that I have got here is positive. That means whatever number I'm choosing in that interval, I will get something positive. What does positive mean? That means the function that I have got is concaved up. The cup shape is concaved up, okay? It's faced up. Okay, if I put 1 into here, 12 multiplied to 1 is something positive. 1 minus 2 is something negative. Negative multiplied to positive, so I will have negative values here. So whatever number I'm choosing between 0 and 2, I will get something negative. What does negative mean? That means the function that I have got when I'm sketching the graph of it is concaved down, okay? Now I'm putting 3 into the factorized form of the second derivative. So if I put 12, into x, put 3 instead of x, I'll get 12 multiplied to x, that's equal to something positive. 3 minus 2 is something positive again. So the result is again positive. Since both are positive, so whatever I have got here will be positive, and that gives me what? Again, concavity, which is facing up. So that is concaved up, okay? Now we are looking at the inflection points. These two will or will not become an inflection point, okay? Is that an inflection point? Yes. Why? Because we said a point like that becomes an inflection point if concavity changes from left to right. Changes, that means either from up to down or from down to up. Here, if you look at it, it changes from up to down. So that is an inflection point, okay? If you look at 2, concavity again changes from left to right. That means it's changing from down to up. Since it is changing, so that one is also an inflection point. Now, what have we done so far? We have found the domain of the function, intercepts, symmetry, asymptotes, f prime, f double prime. We have to plot some specific points. But before plotting some specific points, I have to do a diagram, mixing up the 5th step with the 6th step so that I know how to sketch the graph of the function, okay? Or let me write here. Here, okay, I will do a diagram, not a diagram, just a real number line, okay, a diagram of R, putting f prime, how shall I write it, mixing up f prime and f double prime procedure, okay? When I say f prime and f double prime, that means I'm mixing up concavity and increasing, increasing, decreasing points of that one. Okay, let me move to the diagram, okay? Let me first do the real number line, because that's what I need for sketching, summing up all the things that I have got, okay? Or I can write it here, sum up, okay? Here, sum up all what you have got in the 5th and the 6th step. Okay, if you look at the first and the second derivative of the function, what are the points that I have got? I have got 0, 3, 0, 2. So in general, what do I have? I have got 0, 2, and 3. Okay, what is common, or the union of those points? I have got 0, 2, and 3. I will put those numbers on the real number line. Okay, so I will have 0 here. I will have 2 here, and I will have 3 here. Okay, I'm putting those numbers that I found here and those numbers that were in the second derivative on the same real number line. Now I will see from negative infinity to 0, the function is decreasing and concaved up. Okay, I will write it here. Okay, it is decreasing, okay, and concaved up. Okay, so it is negative here and it is positive in here. Let's check from 0 to 2 if the function is increasing, decreasing, concaved up or down. Okay, from 0 to 2, it's true that I do not have 2 here, but I know from 0 to 3 means from 0 to 2 is also the function decreasing and concaved down. So here the function is decreasing, okay, and concaved down. That means this one is also negative. From 2 to 3, let's see if it is positive or negative. Of course, 2 is here, okay? So from 2 to 3, the function is again decreasing, okay? It is decreasing. And let's see from 2 to 3, of course, 3 is here. Of course, since it is concaved up from 2 to infinity, so that is also concaved up from 2 to 3. So it is concaved up. Okay, I can write it also this one like that. That's up and that's down. That is up. Okay, so we know from 2 to 3 the function that we have got is decreasing and up. Look, we are summing up, or we are mixing the fifth and the sixth procedure to get something. Now from 3 to infinity, the function is increasing and it is concaved up. Okay, it is increasing, that means positive, and concaved up. Okay, that's the sum up. Look, it is increasing and concaved up. Okay, as we have summed up the procedure that was in the 5th step and the 6th step, what will I do? I will see what does that mean if it is decreasing and concaved up. How will the shape be in general? Decreasing and concaved up, it will be something like that. Okay, the function's shape will be like that. So wherever it is, this one, if you look at it, it is decreasing and it is facing up, if you look at it. Now, decreasing and concave down. How can I sketch this one? How will the general shape of that function be? It will be, look, it is decreasing and concave down. It is decreasing and facing down, okay? So this is the mixture between them. Decreasing and down, that's decreasing and faced up. Still, this function is decreasing, that function is decreasing, but this one is facing up, this one is facing down, okay? That is the general procedure for it. Okay, now I have got decreasing and concaved up. Decreasing and concaved up, it will be like that again, okay? That's the general shape for the function from that interval. This one is increasing and concaved up. Increasing is going up, concaved up is facing up, so that one is increasing and concaved up. So the general idea for this, for sketching the graph of the function is obvious right now. So what do I have to do? I have to plot the points, okay? That was the sum up, okay? Or the general shape. I can also name it as general shape, okay? General shape. Now I know the general shape or the sum up of the procedures that I have done. What do I have to do? I have to plot the specific points. Before plotting the specific points, I will find the points that I have got. If I put 0, okay, these points that I have got, I will put them in the function itself, okay? So I'm finding f of 0. I'm finding f of 2 to see where these points are located, and I'm finding f of 3. F of 0, if I put 0 in the original function, what will I get? Where was the function? Okay, if I put 0 into that function, what will I get? I will get 10. Okay, so that will equal to 10. So, 10, sorry for that. So what is the point that I have got? When I put 0 into the function, I will get 10. Okay, that's x-axis and that is y-axis. Now, if you put 2 into the function that we have got, that means 2 to the power of 4 minus 4x, 4 to multiplied to 2 to the power of 3 plus 10. What will I get? If you calculate it, it is an easy calculation. You will get minus 6. So what is the point that I have got? I input 2 into the function, I got minus 6 out. If you put 3 into the function, of course, it will be 3 to the power of 4 minus 4 multiplied to 3 to the power of 3 plus 10. You will get minus 17 out, okay? Minus 17 out. So what is the point that I have got? It's 3 and minus 17. Now, we will sketch, we will do the Cartesian coordinate. We will plot those numbers and then sketch the graph of it. Okay, now if you look, this is the Cartesian coordinate that we have got. We also have got the points. Okay, what are the points that we have got? It is 0 and 10. Okay, it is 2 and minus 6. Okay, 2 and minus 6. The point is here. That is 2 and minus 6. And the other point is 3 and minus 17. These are the points. Okay, now let's sketch the graph of it depending on this one. The function that we have got is decreasing and concaved up from negative infinity to 0. How is the graph of it? It is like that. We have sketched the graph of it. Okay, it is like that. Look, I'm giving the same shape to this one. From 0 to 2, that means from here to here. How is the graph? Look to that point. The graph is shaped like that. So I will sketch the graph of this one just like that. Okay, look, I'm giving the same shape from 0 to 2. Okay, from this point to that point, it is face down and like that. Now, from 2 to 3, from that point to that point, how is it? It is again that shape. So I'm giving that shape to this point. Okay, although it is not very obvious here, but I'm doing my best for you. Okay, from 3 to infinity, how is the graph of this function? It is that shape. So I'm punching it up, and it is something like that, and it's going to infinity. That's the point 3, 2 minus 17. So this is the general sketch of the graph of the function. So that sum up is the most important that you're doing for that function. You're doing all that procedure to have the plotting and this sum up so that your sketching will be very good. You've got another example for this procedure for sketching the graph of the function. It is solved in your lecture notes. You can do this one as a practice for yourself. I hope I could have done the best for you to understand the subject. I think it's easy. It's just the sum up of the mathematics that you have studied so far. I hope you would enjoy watching it and understand every single word that I have said. Have a good time.